hear about the importance of machine learning and AI for applications, and the previous speakers made good excellent cases for, with all the data that we're collecting, why it is important to really understand like what machines can do with that. I mean, you've heard the saying, software eating the world, AI, ML eating the software. And so I'm really excited to hear the next speakers of how this also applies to the cybersecurity domain. And it's my special pleasure to introduce the first speaker, Rachel Greenstadt, who will be speaking on using stylometry to attribute programmers and writers. She's an associate professor in computer science at Drexel University, where she founded the Privacy, Security, and Automation Lab. She received an NSF Career Award and a PET Award for Outstanding Research in Privacy Enhancing Technologies. So please give it up for Rachel.
Okay, so my talk was apparently called out as the one that was incomprehensible, so hopefully will be comprehensible, but we will have a bunch of some technical stuff to talk about, so that's exciting too. What is stylometry? This is the idea on this is that everybody's writing style is unique, right? We all speak a little different, whether it's because of regional differences, whether we say couch or sofa, or sub or hoagie or sandwich for Philly people, it's hoagie. Maybe there's spelling differences, especially on platforms like Twitter or in online forums and things like this. Maybe we use similar meaning words that actually are different words, like although versus though, or toward or towards. And then there are a lot of different ways that we can express the similar ideas, but in different ways, like the fork is to the left of the plate, or the fork is at the plate's left. So we actually have a lot of really great techniques that we've developed in the security community over time for location privacy, Tor, mixes, things like that. But maybe they're not enough, and that's what I'm arguing, because maybe it's possible to identify authors based on their writing, and this is a potential threat to people exposing crime and corruption and doing political organizing, but also to normal people who are just interested in sharing their opinions and maybe their code online. So there is actual real-world impact about this. Some of you guys may be fans of J.K. Rowling. She wrote a series of books called Harry Potter. But she also wrote a crime novel under the pseudonym Robert Galbraith. And there was a reporter, Cal Flynn, who received an anonymous Twitter sort of tip that J.K. Rowling was the real author of this novel. And, typically reporters are not willing to go to press based on anonymous tips over Twitter about stuff like that. So they actually had analysis done by some of my collaborators, Yola and Associates, to determine that the writing styles were similar, and then they were willing to go to press, and it turns out that yes, these are the same people. Our doppelganger finder code, the algorithm developed by Sadia up here in the front row, is designed to give the probability that two accounts are the same person. And this is actually being used actively by the FBI in investigations. They haven't given us many details, but they have told us that it's useful. And it also governs sort of legal evidence. In many places around the world, in the US, the use of stylometric evidence is governed by the Van Wyck opinion that says that you can discuss the similarity of writing style as evidence in court, though you can't say like the computer said it's this person. So most methods that do stylometry these days use machine learning. So say we have two authors here, Cormac McCarthy and Ernest Hemingway, and we want to attribute an unknown piece of writing to one of them. So we take some of their writing and we extract features from it. These may be punctuation or function words or other types of things like this. And we build some sort of model out of this using learning. And typically we want 4,500 to 7,500 words and over 1,000 different types of features to do a really good job at being able to do this. And then we have our test document. Just remember that the things you put in your head are there forever, he said. You might want to think about that. Is it Cormac McCarthy? Is it Ernest Hemingway? Well, hopefully we have more than just this little sentence. Hopefully we have 500 words or so. And we ask the model who wrote this, and it tells us that it is indeed Cormac McCarthy. So this is the idea behind this. And current methods are pretty good. When we're talking on the scale of less than 100 authors, they're really quite good in the 90 percentile range and so on. And you can scale it up to people have looked at 10,000 authors, 100,000 authors. Accuracy goes down, but it doesn't crater, basically. But because we're security people, there's this question that you might ask of how reliable is this really? Can stylometry be attacked? How easy is it? And we did a sort of a study attacking many methods of stylometry, and we found that it actually, when people try and hide their writing style, they're able to do so. So we looked at a number of stylometry methods and scaled things up, and many of them are quite accurate. But then when we ask people to write an essay hiding their writing style, the accuracy goes basically to random chance. And it turns out that it's even worse when we ask people to imitate an author. We'll use Cormac McCarthy again because he has a nice, dark, vivid writing style. So we ask people to talk about their mornings in the style of Cormac McCarthy, and we get sort of statements like hot water in the mug, brush in the mug, the blade red Wilkinson sword on the layered wax paper packaging. So we have these sort of gritty tales of getting coffee and staggering out of bed. So then the question is that we had also was not just, okay, so these things don't work well when people are trying to fool them, but in lots of cases people aren't, and maybe we can use them to learn things about cyber criminals. So we found a bunch of underground forums, and we wanted to apply our techniques to them. And this turns out to be a little bit tricky. You have to make some adjustments for the fact that they're not in English. And people use things like leet speak and so on. But we were able to do that. And what we were able to do was, one thing we were interested in is in a lot of these forums you have multiple people that are actually the same person. And we want to figure out if the same person has these two identities and that they're actually the same person. So we developed an approach to calculate the pairwise probability that each author is actually a different author, and train a classifier on those and figure out we'd get a prioritized list of which authors are the same. And it ends up looking like this. This is a Carter's forum that is a sort of German forum that's specialized in trading credit card information and other like banking credentials and things like that are stolen. And you can see the probabilities of each pair that being the same kind of start out very high and drop off. And what this does is it allows you to manually analyze these high probability pairs and learn things like the pair with the highest probability seems like definitely the same person, right? User 1's account was banned. User 2 asked them to activate his other account again. And the pair with the second highest probability had the same ICQ number. They both sell similar things and so on. And we were able to pretty much validate these high probability events. Pair 21 was an interesting example where they actually share each other's accounts. So it's two people, but they are using the same account. And so it was sort of intermediate thinking that they were the same person. And they actually talk about the fact that the forum bot thinks they're the same person. So there's also this case of maybe we can use this approach to link identities not just in one particular domain of underground forums, but maybe across domains. We have people using Twitter and people who discuss things on blog and Reddit, and usually you use quite a bit. These are actually the same person talking about music in a very different style, but still the same person. And we're interested in, can we link these identities together? So in this case, we're looking at, say, Twitter and Reddit. And what we'll do there, and this is basically how this doppelganger finder type approach works, is it averages, right? So it doesn't just look at one tweet or one blog post or whatever. It looks at an account and it splits it up into pieces and kind of averages the results across them, because we know that, and this kind of allows us to boost the accuracy of the learning algorithm. We're also able to train, because we're training on all pairs, so we train on basically all the Twitter accounts and all the Reddit accounts, and we look at the combined probability that A wrote B and B wrote A. And this allows us to kind of take information from both pieces and get much higher accuracy. So if you see like the naive approach where you just train on one and test on the other, gets you like 40% accuracy, which isn't great. Individually, we're at that around 90% accuracy range. But we can recover a lot of this accuracy by using these averaging and then ensembling approaches back up to about 80%, and are able to get this sort of linkages between these really quite different mediums of expression, and in a way that is nice for people to be able to look at. So, okay, that's nice and kind of scary, but I said that it was possible to hide your writing style. How do you know if you're doing that right? If, say, you do want to write something anonymous online. So we've written a couple of tools in our lab. JStylo is a nice tool, especially for the students in the room, if you want to play around with actually analyzing people's writing. I know there were some students at Drexel that were interested in doing that, to analyze like political speeches from the most recent election and things like that. Or to write anonymous documents. We have a tool called Anonymouth. And it looks like this, where you put in sort of your writing and a bunch of other people's writing that you want to blend with. And it will usually, do its learning in the background, and then it will usually tell you, yep, it's you. But it will give you some advice about words to add and words to remove. Some of them may be hard. It's like, you're really using the word the a lot. Maybe you shouldn't do that. But you should be able to over time, be able to reduce the certainty and perhaps get it identified as someone else. One of our lab members actually did this with a number of different famous writers, turning them into anonymous hacks using his software. And we actually have a tool, Warden, which is a little more lightweight and easier to use. It's web-based, but it's not up anymore, but it's on GitHub, and you can play around with it if you're interested. That can help you understand roughly why things get classified one way or the other. So, whenever I talk about this, people always ask me, especially in rooms full of computer scientists, which this mostly is, I think, what about code? Who wrote this code? Does it work on, code for, someone? Does somebody know that this Git commit was me? And so on. So we did some work looking at the Google CodeJam programming competition. We used that as a data set, and we parsed all the code into abstract syntax trees. I'll talk about that representation. And then we used random forest classifiers to classify the results by majority vote. So abstract syntax trees are basically a representation of the structure of the program. In the past, when people had tried to do stylometry on code, they mostly used sort of n-grams in the source code and layout and reserved words and things like that as features. We do that as well, but we are able to get much, much better results by incorporating these structural features. They're also much harder to obfuscate. And we use this data set, mostly the C and C++ code, so we now have some results on Python and JavaScript. In these cases, they're nice and controlled. Everyone's implementing the same functionality for a certain problem at the same limited time period. We can train on these and test on a problem that we are not seeing in training. And we get pretty good results. We kind of can frame them as sort of a large-scale anonymization of 1,600 programmers, which we get 93.6% accuracy. If we're interested in a much smaller situation, like a copyright investigation, where two people claim to have written the same piece of code, then that gives us like close to 100% accuracy. Or we can think of open problems where we think it's maybe one of 30 programmers, but it could be anyone in the world, and we want to allow for that possibility. We still get very good results in those cases. And these are we get much higher accuracy on much larger scale than previous work. So a lot of code is collaborative. We've got some recent results looking at individual Git commits and actual repositories in the wild. We get about 70% accuracy on each given fragment. But for accounts, just like we did doppelganger approach, we can aggregate them together and average the results, and we get much closer to 100% accuracy once we do that. And we also have some cool results on binaries, where we're actually, compiled code seems cryptic. You'd think it would add some obfuscation, but when we use disassemblers and parsers of the control flow graph and use a combination of the stylistic features on the source code and sort of blocks in the control flow graph, we're able to do almost as well, not as well as the source code. We can attribute 600 binary authors. These are the same. This is the same data set, just compiled with about 83% accuracy, much higher if it's a smaller data set. And we've done some interesting real-world attribution. It's harder to do with things like GitHub because we often don't have as much training data, and that's usually why the results are worse. We just find like this one repository, but when we do have, but that seems to be the effect when we are able to get large data sets that are the same person, we do pretty well. And we also were interested in applying the binaries to actual sort of exploit code. We've done this work on cybercriminal forums. Sometimes in these forums, people actually trade exploit code and malicious software. And we were able to have, we found 4 users in the null.io forum, and 3 of them had enough data to train a model. So we were able to correctly identify those 3 person, and we were able to use the open world method to show that the 4th person was a different person. So it works pretty well. And in conclusion, anonymity is hard. It's not only about what you write, but how you write it. Stylometry can combat online abuse, but it's an anonymity threat itself. And we're actually surprisingly good at de-anonymizing data and text across a lot of different domains. So it's an interesting sort of thing to play with and also has impact on the world. Thanks to all of my collaborators. This is far from done alone. And here is some information if you are interested in looking up some of our code and projects. And I think I might have time for like one question. I don't know.
Thank you so much. Yes, so we have time for 1 or 2 questions. I think you were the first one.
Hi. How did you approach deciding on what model to use for the, what machine learning algorithm did you use, and how did you decide that, and to keep it neutral to best match with people? Because I had an issue figuring out what to do for like text generation from people, so it's, yeah.
Yeah, it's a model choice is always, it's always tricky. There were there's a number of different options out there. When we were trying to attack stylometry, we mostly used what other people had done, sort of the best state of the art. That wasn't really a choice. When we were doing the doppelganger finder work, again, we kind of picked the, used support vector machine type models, linear models. They've worked pretty well, and then we built on them with the sort of our ensemble methods on top of that. When we were doing the code, however, we really wanted to be able to handle overfitting well, but also have interpretability to be able to understand what was causing these results. And that was why random forests are great, because they're an ensemble, so they have a lot of they're pretty fast as well, and they have a lot of interpretability. We have done some work using deep learning on the abstract syntax tree that is able, when we just use the abstract syntax tree features, to do better than using the abstract syntax tree features with the random forest model. But the thing is, our handcrafted features that we add in addition to that sort of make the random forest overperform. One of our next steps is kind of combining those 2 approaches. I think these days deep models are great when you have a lot of data, and when you have when that data is very sort of can be handled when you don't have a lot of hand-coded domain stuff to add into the model. When you do, you might need to do something kind of in between, if that makes sense. Hopefully that helped.
One last question.
How did you move like the authors from like a source control system into like the abstract syntax tree? Like, did you avoid using commits that had code by lots of different authors, like striped multiple times, like every other line was written by a different author or so on, like that?
So, yeah. So all of the work that I was presenting earlier was sort of single author stuff, which is one reason it's hard to find. It's hard to find GitHub repositories where only one person is writing. The git blame who stuff is actually collaborative code, and we used git blame to segment things, and we looked at, and actually the parser that we're using, the Yorn parser, actually works on incomplete code segments, so we can actually feed in the incomplete code segment. When it's one individual line, results are not great. But when you have like function level stuff, things are doing well, and we actually have some work in progress on actually like looking at like how big those abstract syntax trees need to be and how that affects the actual accuracies. So.
Okay.
I'm gonna give Becca.
Thank you so much. Let's thank Rachel one more time for the great talk.